Okay, we're going to talk about Kepler's laws real quick, okay? And I'll show you the proofs of them too. In Physics 1, we didn't do the proofs because they were a little too high level at the time, but now we can do, well, I think we did some of them in Physics 1. I can't remember exactly. Um, okay, Kepler's first law says that all planets move about the sun in orbits that are ellipses. So, um, you've done circular orbits, but that's actually not true. There's all orbits, at least for planets and stars, move in about ellipses, right? And the sun is at one focus of that ellipse. Okay. So, for example, if you have your ellipse right here, right? Okay, that's a terrible ellipse, but your sun is going to be at one of the focus of that, one of the foci of that ellipse, and then the planet is going to go around the ellipse perimeter. Okay. In reality, if a small mass m is subject to the gravitational field of a larger mass big M, the trajectory of the smaller mass is going to be a conic section. Conic section. Okay, which one of the conic sections depends on the value of the total energy of the object in its orbit. In either case, the larger mass big M resides at the focus. Okay, so either way, the larger mass is going to be at the focus of the ellipse or the conic section. Now, conic sections, I do not believe, are within the scope of Physics C anymore. I don't believe they need to. That shouldn't be in there. You're not going to see any questions that pertain to the different conic sections because you don't learn conic sections in the math classes that lead up to Physics C or the ones that go with Physics C. I don't believe you do them in AP Calculus, and I don't think you do them in pre-calculus anymore. When I was in high school, I did conic sections when I was in pre-calculus, but it's been for I've never had to do conic sections a day in my life after that. So you can see these are just examples, right? If the total energy is these things, then this is what the conic section is going to be. You don't really need to know that, but that's just kind of if you're curious, okay? Kepler's second law is my personal favorite one because I kind of like I just like it, right? It says that a line connecting the planet and the sun sweeps out equal areas in equal amounts of time. So that's saying that, for example, a planet that's orbiting right here, okay, it completes this trip right here in a segment delta in a time interval delta t, but it's also taking that same interval delta t to complete this part right here, and it's taking the same delta t to complete this part right here. So all of these areas, they're all identical to each other. Okay, you can think of this one because it has a rather lengthy base. Okay, but the height is not very much here. Smaller base but a larger height. Here, really small base, really large height. Okay, so that those areas should all be equal to each other. This is actually a statement on the law of conservation of angular momentum. Okay, and I'll show you that. Momentum. Okay, there's actually a statement on the law of conservation of angular momentum. Okay. So I want to show you this. This is for a circular orbit, and it does apply to elliptical orbits as well. Okay, but it's just easier to show with a circular orbit. Okay. Um, in this case, okay, the let's say that we have a planet orbiting, um, orbiting in a circular motion. Okay, if as it goes from here to here, okay, it sweeps out some area dA. So this is the amount of area that's already been swept out, and the amount of area A that's been swept out is changing by dA every so often. Okay. In addition, this is the angle that we've already swept through, and we're increasing the amount of angle that we're sweeping through by an amount d theta every so often. Okay. This distance right here is r. Okay. And we can approximate this as being a triangle but I need to figure out the linear length right down there at the very bottom. So what I'm going to do is I'm going to call this, we can say that this part right here that we've already swept through, this is arc length S, and that's changing by an amount ds every so often. Okay? ds is going to be equal to r times d theta because s is equal to r times theta. Okay? So there's that, right? Okay. So I can, when I write out an expression for this, I can then say that the amount of area that I'm sweeping out, okay, is equal to 1/2 r squared theta, okay, because this is really, let's see, if I'm going to consider the triangle here, right, this is, so the amount of the area that I'm sweeping out, dA, is just going to be equal to 1/2 base, okay, the base is r times d theta, okay, and then times uh, the length, which is r, okay, 1/2 bh, right, and then the r's multiply together to give me that the dA, the amount of area I'm sweeping out, is 1/2 r squared d theta, and I guess and I'm just rewriting that to get a, right? Okay, I'm just taking out the d's and everything. Okay. Okay. Well, what's important to understand is that to actually, let me get started on the actual proof of it, is that if I have dA over the, so this is the area that I'm sweeping out over a period of time, this should be constant. Okay. So I'm kind of assuming that this is true in the proof, okay, and I can prove it from there. Well, dA I already got is 1/2 r squared d theta over dt. Okay, this is constant still. Okay, well, I recognize that this is just 1/2 r squared d theta over dt, which is still constant. Okay. Okay, and then I recognize that d theta over dt is just omega. Okay, so I'm going to then do, let's see, 1/2 r squared omega equals a constant. Okay, now here's what I'm going to do. Okay, if I want to get, I can actually turn this into the centripetal force equation by multiplying by 2m on both sides. 2 to get rid of the 1/2, and then m to add an m to this. And that's exactly what I'm going to do. Okay, I'm going to do, so I'm going to multiply both sides by 2m. Okay. And this is going to give me, so my 2 and my 1/2 will cancel out. That's going to give me m, oh sorry, this is not going to give me centripetal force. It'll give me the angular momentum, right? So this is going to be m r squared omega equals a constant. By the way, constant times 2m is just a new constant. Okay. And mr, right? Mr squared. Well, if you think about it, a planet is really just a point mass at the end of a radius. So that's basically the moment of inertia for the planetary motion. Okay. So this part right here is going to be I. This part right here is, you guessed it, omega. And then this right here is our new constant. Okay. That's how we're showing. We're basically showing that it's angular conservation of angular momentum. Okay, so there's that, right? It's showing that this is constant. Okay. Okay. All right. The last thing I want to go over. Why is my paper just okay? The third law says that there is a ratio for all planets orbiting the same central body that's constant, and that is going to be t squared over r cubed. Okay. T is the period. R is the orbital radius. Okay. This is very, very important that this only applies to circular orbits. Okay, so not for ellipses. Okay, so do not use this for elliptical orbits. This ratio must stay the same for circular orbits. To prove that to you, I'm going to show you that I've got capital G, little m, big M over r squared, and I'm going to set that equal to m omega squared times r, okay, to prove to you that the ratio only depends on the central body. It doesn't depend on what's going on with the other body. It doesn't matter if you're radius r away or 4 times r. That's going to, it's only dependent on the central body, okay? Okay, I can cancel out my little m's. And then here I can divide the r onto the other side to give myself r cubed. And that gives me omega squared is equal to g big M over r cubed. Okay. Okay. If I set that, I can then actually substitute the omega here for being 2 pi over t. Now it is going to be squared, which is fine. Okay. I can do that. I don't have to root it here. So this is going to be 2 pi squared over t squared equals g big M over r cubed. Okay. Well, the numerator is just going to be 4 pi squared over t squared, and then equals gm over r to get t by itself. Or actually, I don't even need to get t by itself. Okay. I need to get t over r on one side. So I'm actually going to multiply by t squared and divide by gm. Or you can kind of cross multiply that a little bit, right? So I get t squared over r cubed equals, equals 4 pi squared over g big M. Okay. Now, do you notice that this ratio right here, t squared over r cubed, this is not dependent on anything that the little mass does. G is constant and big M is the mass of the larger mass, the central mass. So there's not really anything that little mass can do to change this ratio. Okay. It only depends on, so if you notice, right, only depends on central mass. Okay, so if we were to change something about the central mass in some way, awesome, cool, but you know, that's all dependent on that. Okay, and then for elliptical orbits, so that ratio doesn't apply to elliptical orbits, but for elliptical orbits instead, you can use the ratio t squared over a cubed. A represents the length of the semi-major axis, and the semi-major axis is the longest radius of ellipse. Okay, so what that means is that if you have an ellipse, which is going to maybe look something kind of like this, okay, that's still a terrible ellipse, and let's say that like my star is right there, okay, or the sun is orbit is right there, then what you're going to notice is that this right here is the semi-major axis. Is this right here? Okay, this distance. Okay, this would be A. All right. Yes, there is another radius right here, the smaller one. Yes, there is more radii up here and stuff, but they're not really important. It's really just this semi-major axis right there is the most important. Okay, that is Kepler's laws. Okay, we'll be back with some more stuff soon.